All right, I'm going to turn my volume too because it's a little low. Okay, so all right, so this is kind of continuation from, I guess it was on Wednesday, from section 29. Like I kind of mentioned before, I know Barbara kind of came in a little bit later. Section 30 is much more like a review of like combining a lot of stuff together. So I'm not going to really go over anything specifically from there. But we're going to focus mostly on the last half of the evaluation or evaluation metrics and stuff. Okay, so I'm going to share my screen and then I will, let's see here. We'll kind of review a little bit of what we talked about, and then we'll go into the actual section that I want to talk about, or not the section, the topic that I want to talk about. So just kind of reminder is that, was it last time we actually talked about, let me move you guys over here so I can see you all when I'm talking. All right. What was I saying? Oh yeah. So we can talk about, like, we looked at logistic regression and then seeing how that basically introduces us into classification. So we've been using logistic regression. Just know that this also applies to any classification. Well, any classification that you want to, not just logistic regression, which we'll see in the future. But essentially we talked about saying basic classifications, a yes or no. You're either with us or against us. So you can imagine if you have multiple classes, essentially you're saying it's either group A or not group A. And then you'd be, is it in group B or not group B? Or is it in group C or not in group C? That's essentially how we can make it binary, right? We kind of recalled the linear regression, how it connects with logistic regression. So this is one strategy. We talked about how implementing logistic regression. So I'm not going to go through that whole thing again, but you can remember we built up our logistic regression with sklearn. We performed these parts. We can see like our accuracy, but we talked about saying, well, accuracy might not be the only thing, just saying how true you are. You want to see a little more detail of, like, you know, well, okay, like of the things that you got wrong, like either you marked as negative, even though they were positive, or they marked as positive, but they were actually negative. Did I say the same thing twice? But like if you have the part, you want basically say like, well, what gets deeper into that? Like, how are we making a lot of false positives or making the false negatives? You know, what's our accuracy, like beyond our accuracy? So we talked about some metrics. We talked about confusion matrices and other metrics. So in that one, just kind of quick review. We talked about precision versus recall, as well as actual accuracy. And then combining precision and recall, we can get into our F1 scores. There we go. Our F1 scores and our F beta scores, right? Basically putting out like which one's more important, right? Precision or recall. F1 score means basically they're both equivalently important. F beta, basically, as you increase beta, you're increasing saying, well, recall is more important. And this might depend if you care about type 1 errors or type 2 errors more. Okay. All right. And then we talked about confusion matrices. So I'm going back to, like, you know, how we define precision recall. We can look at a confusion matrix. We talked about an example like this one, basically like saying how on the diagonal, basically those are like essentially making it like, you know, you got the right thing, you got true positives, right? And see the percentage and how well it does here. And then you can find these little islands that are not doing well. So you can identify where it's making false negatives. So this is really nice going through. Now, one issue with this, which is what leads us into what we're going to talk about today, is that if I want to compare, like this is, for example, one model is the VGG16 model for transfer learning for this particular, this particular project that I had done. Compared to this one right here, it's not really easy to like directly compare it like back and forth. And you can imagine if you have multiple models, it's kind of difficult for us to go back and forth and say, okay, we did this well in this part, but how well did we over here? So one alternative to this is something called our ROC curves, or ROC curves and AUC, which AUC stands for area under the curves. These are related together. So we're going to talk about those. So, all right. So one thing we kind of go into before we talk about like how to do a ROC and stuff like that, our ROC curve, which stands for receiver operating characteristic curve, which I have to be honest, I don't even know how to approach that. I usually can break things apart like in like how it's said. It's just very intimidating more than anything. So don't stress out trying to remember this. Most people, you say ROC, R-O-C, they know what you're talking about. So just kind of be aware of that. But one thing we want to basically do is we really want to compare the false positive rate versus the true positive rate, okay? So essentially we're doing something similar in the sense of confusion matrices, but we're modifying it just to say a false positive rate and a true positive rate versus like having multiple classes and stuff like that, okay? So kind of quick questions, like if we had a classifier, imagine like saying either yes or no, or true positive, or group A or not in group A. what's the worst kind of classifier we could have? Like how would the worst classifier actually perform? You got an idea what that might look like? Yeah. So like the best classifier, right, would be like if it got it every single time. So like if it understood like, oh, that's in group A. Oh, that's not in group A. Okay, that's true, that's false. That's true, that's false, 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 true, right? Perfect classifier. What would be slightly worse than that?
The opposite to that. So it
Opposite.
gets it wrong all the time.
Yeah, so maybe if it's true, it actually says false, and if it's false, it's true, right? So you would think that would be actually the worst classifier, right? But it turns out if you think about it, it's actually not that bad, because if you know it's always going to get it wrong, like it literally always gets it wrong, that's actually like a good thing, because then you always know it's just the opposite of that. So it's kind of like the way I describe this is like if you have a friend or maybe an acquaintance that has a very different like, taste in like movies or in books or something like that. And every time they read this certain book, they're like, oh, I hate this book. And every time you read it, you're like, wow, I love this book. And then every time you said, oh, I love this book, you read it, you're like, oh, I hate this book. You know that they're in a sense like one of the best recommenders because you basically just go opposite of them, right? So in a lot of ways, they're actually not that bad. So actually the worst kind of classifier in a lot of ways, it's just random, is that if it just basically just guesses every single time, so it's got a 50-50 shot of getting it correct, that's actually our worst classifier. What is nice is that when we do gradient descent, we tend to go towards better than guessing. So the whole idea usually is our base model is actually guessing, and then we go off of there. What's nice is that we don't tend to go the opposite direction where it constantly gets it wrong. It usually is in that other way, because if it's always getting it wrong, it's technically learning something, we're just learning it in the backwards. So we can always count for it to move forward in that way. Okay, so again, the worst classifier is just guessing. So we're going to see this kind of show up in our ROC curve in this bit. But remember, like a bad classifier is even if it like guesses completely wrong every time, it's actually an amazing classifier, just the opposite of whatever they have. Okay, so now it kind of comes down to just like, okay, like kind of talk about, all right, we know what kind of like what the worst kind is. We have an idea of like true, false, positives. Now it comes to like, let's tie this together with actual logistic regression. So I'm going to draw logistic regression right here. And you know what? Actually, I'm going to draw it in this app right here. Oh, this should actually be just right here. I made a mistake. This is just so I can draw stuff. All right. So if you remember logistic regression, right? Looks something along line. I'm going to use black just so it stands out really well. Okay. Our logistic regression. Nope. Come on. There we go. Okay. So we imagine our logistic regression looks something like this, right? And remember that basically on the side here, it's saying it's either, let's say, true, 0 or 1, right? Or 0, which is false, right? And then this is some, let's say this is some metric right here. It's just some feature X, right? So these can be multiple features, but the idea holds. And then we have actual data points. Let's say these, for example, are negative. So they are in fact false. So we'll have like X right here. There's a data point here, data point, maybe data point, but most of them tend to be, on this end. And then we might have something like, these are all the positives. So there's a couple of positives that are on this extreme end, but most of them hang out over here. Something like that, right? Okay, put one right here. All right. So this logistic curve basically is going to predict the probability of it being in the certain group. Now here's the big trick of this is that, well, we can say along this curve, remember this goes from 0 to 1, right, along this x-axis, and it's hyperbolic, so basically it'll go off to infinity. So if your x factor like goes on to like 1,000,000 from like 0, you can do that. It'll just keep going forward, right? It'll just be more and more likely that it is true, right, in this positive part. So the thing is, this will give us the probability. So if I'm like saying, okay, if you have a, let's say, this is, I think last time I used the thing of weight and like if you have heart disease or not. So let's say like, this is like, if you have heart disease is true. So this means your heart is bad, right? So you have heart disease, right? So you have heart disease and this is like your weight. If you have a weight of, let's say like 120 kilograms, okay? Then we go up to here, it's like, okay, that's like a 70% chance, right? That you have 70% chance that you have heart disease, okay? That means if there's something right here, you are likely to have heart disease over the other part. This is where you have to decide though, if someone's at like the 50% chance, like do you move them to not heart disease or move them to heart disease? So you can kind of envision this as like drawing a line straight through here, okay, and saying, okay, everyone to the left of this is going to, we're going to say it has heart disease, and everyone to the right of this, we're going to predict to be everyone to the left of it say we predict they don't have heart disease, and everyone to the right of it says they do have heart disease, right? So essentially we have to make this cutoff at some point. We call this like our threshold, right? So at a 50% mark, you might change it. But maybe you want to adjust this. Maybe you're like, you know what? Like if we're going to say someone's going to have heart disease, we should move it really close to the side. Like maybe we want to make sure we don't accidentally diagnose someone with heart disease when they don't have it, right? So you might actually move it from 50%, you might actually move it closer to like maybe like 80%. So maybe something like right here, okay? So in that case, like that would be like, you know, at 100, I don't know, let's say 160 pounds or kilograms, right? And go from there. Say, okay, everyone to the right here, we'll mark those with heart disease, and everyone over here, we won't have heart disease. Well, that means that you're gonna have some false negatives, right? Because these actually do have false or heart disease, but you didn't catch them. And you can argue that something seems like, well, if you wanted to catch everyone who might have heart disease, we want to make sure we diagnose them, you'd put the threshold closer to over here. So maybe even if you have a 10% chance of having heart disease, based on this model, we'll say, okay, no, you definitely, like, we're just gonna classify you as having heart disease. So you basically will get more false positives, but maybe that's something that you prefer. So you can imagine moving this threshold back and forth to figure out basically like, well, how many false positives, how many false negatives you want, right? So remember, this is just all based on this one model. So you can imagine moving that threshold, and that will give you different recall and precision depending where you draw that threshold. Does that make sense? Okay. So one big thing about this is that you have to realize is that it all depends on the, well, first of all, we have this model and we're drawing this over. A factor that actually says like, hey, are we going to have more false positives or more false negatives is that how much crossover there is. You can see here is, well, let me ask you guys looking at this picture of this data, is there any way we can draw a threshold so we always get exactly, we get no false positives and no false negatives? Any straight line we can draw? No, yeah, right? I'm sorry?
Could it be a diagonal line?
No, yeah, in this case, we actually have to draw like a straight line because we have to say at a certain weight, what do you do, right? In some ways, if we had multiple features, we essentially are drawing a diagonal line, but if we put in all the features together, essentially we still have to draw one line, say, what is the cutoff, right? There is some percentage at a certain point we have to cut it off at. And so, yeah, I think, but if we could do that diagonal, you could do this, but since we have to do a straight line, there's no way. I saw a couple head shakes being like, yeah, there's no way we can draw a straight line. We're always gonna have some false negatives and false positives. So you can imagine it depends on this distribution. If it's more or less random, if it's like all a bunch of falses and all a bunch of positives here, and they're both equally distributed, then there's gonna be 100% crossover, and you're not gonna be able to ever draw lines through there. Basically, your classifier, your model's never gonna do very well. The extreme of this, or the opposite, is if we had all of these guys right here, like missing, right? And then like if we had perfectly separable, it's like, okay, that means there is at least a possibility of getting all the negatives and all the positives on the correct side, okay? Of course, you can see there's some little crossover here. So there's no matter where we draw this line, we're going to get false positives or false negatives. If I could avoid all of the false positives by drawing it right over here, but I'll get a whole bunch of false negatives. So this is a way we can kind of like, I want you guys to kind of keep that in mind when we look at this next visualization, okay? So this is where, I think this is actually from the curriculum from section 29. And basically what these two different humps represent is the distribution of, and this is our X feature right here, basically all the ones that are actually false, like these are like, they truly don't have heart disease, and the green over here are all ones that truly have heart disease, okay? And you can see there's some crossover here. And you can see there's different distributions. So for example, if I had a group that has very little crossover, so you can imagine like, maybe like this one where there's just like one little true right there and everything else, there might be a little bit of crossover. That would be pretty good. That means that we can separate them out. Like you might make one mistake or two, you know, by putting this threshold at certain points, but that'd be all right. If we have a lot of crossover, like if I had a lot of, like I showed before, like a lot of blue and a lot of red on the side, like crossing over, then we might actually have some things like, well, this might look closer to this, where like you'll never be able to separate this out, essentially. These will always be like, you're never sure if they're positive or negative, is kind of that part. And so what we do with this threshold, like I kind of mentioned, is we draw our threshold right here. And when we draw our threshold, we say, okay, we're essentially drawing a line right through one part right here. So if you imagine like if I drew a line that was closer to this side right here, I might draw like a line. Let's see if I can draw it really quickly with zoom. Okay, if I draw a line like here, okay, basically it's saying, okay, well, these are all my true positives, right? And then right here, these are my true negatives, right? So everything underneath this red curve will be a true negative. Okay, what would this section right be here from here to here, like this kind of triangular section?
False negatives?
Yeah, false negatives, that's right. So yeah, so these are all false negatives. So you can see I get a bunch of false negatives. And maybe for certain applications, that's perfectly fine. If I drew that same threshold and my separability looks like this, you can see my false negatives is about the same, right? Okay, so I really should have drew this threshold right here to get like a better, getting all those like true negatives, right? So you can see I could make the threshold much smaller. So you can depend, you see it can depend on the data itself going forward, okay? So again, we're just gonna move that threshold back and forth until we find a well, what we deem as a good enough true, false, negative, true positive rate and the false positive rate, okay? So any questions on how this relates to what we saw? Okay, and just kind of re-emphasizing back earlier with the logistic, everyone understand like this logistic curve, like how it's classifying if it's true or false. You can imagine if I drew underneath here, let's see if I can do this really quickly. This would be like, it looks something like this. And then maybe for the trues, I have something that looks kind of like this. And that's essentially what our graph is, what we're looking at. And so we're saying, okay, this is the distribution of the actual points. And then this is our threshold going forward. So you can see how many true and false positives we're actually going to have. So you can see here, we'll get some more false negatives here if we drew our threshold right underneath to there. Versus writing it over here, we get a lot less false positive or false negatives, but we'll get some false positives because we're going to get some of this part right here. Okay, everyone understand on that? Any questions? I know there's a lot of graphs kind of going back and forth, but okay, cool. So I'm going to show you guys a little cleaner part where I'm not drawing it myself, because that usually helps because I'm not the best drawer. You can see another part. Oh, I forgot to talk about this. This is another one from the curriculum. You can see something similar where we adjust that threshold, right? As we adjust that threshold, you can see how many true negatives versus true positives versus false false negatives. So you can imagine that like line moving back and forth. And so with that, I'm trying to think how I want to show this next part. Okay, we'll try this. I'm actually going to skip over this part right now. And we're going to go over here so I can show you this guy. So there's this little website, which I found, little web app, is super useful. And so you can see here, and ignore this part right here, this ROC curve. We're going to focus on these actual distributions. You can imagine this right here has a good distribution of positives and negatives, right? So you can see there's a little bit of crossover. So if I wanted all the false positive, or sorry, I don't want any false negatives, I would move this all the way over here, right? And you can see if I have all this right here, I would always get the positives. I would never get a false negative. All the things on the left here are all negatives, right? And I move this over to the right here. That would mean I get all no false positives, but I'll have some false negatives right here. And you can see with this little graphic, I can adjust this part, is that if my distribution has a lot of crossover, there's never going to be a case where I can completely put this. And if it's like really bad, you can see that's like, oh, it's completely crossed over. It doesn't matter where I draw this threshold. I'll always get the same number, essentially a false positive, false negatives, right? So they'll be equal to each other. Okay. So we kind of saw a little bit like how we can draw this part out. We can kind of visualize this for saying, okay, like what if I want to just look at like, where should I draw this threshold right here? And you can kind of see it's being hinted on the side. we can actually draw a little graph of this. And so what this graph looks like, will look like this. And so what happens is this is essentially what's our true positive rate versus our false positive rate. And this is what we usually talk about as our ROC curve, okay? And so what this is going to basically do is it say, okay, like for our distribution, so imagine like each one of these lines is a different model, okay? I want to make that really clear, that each of these are a different model, a different classifier. So let's say this green right here, and ignore like whether it's green is good or excellent or worthless. But if you look at this green, this very top one, okay, what this is representing is like when we draw the different thresholds, what's our true positive rate versus our false, should be false positive. I don't know, it's fake positive, but false positive rate. So you can see here, like imagine if I have a little annotation, let me draw, there we go. Okay, so if I have like a point like right here, okay, what this is saying is like if I, for whatever threshold this is, I don't know what this threshold is like, you know, just based on this drawing, but whatever this threshold is, this bit neat says like, oh, I'll have about a 95% true positive rate, which is good, but I'll also have about a 0.4%, or sorry, 40%, so 0.4 false positive rate, so FPR, right? So you can see here's like, well, that's not quite good, right? Maybe I want something closer, like, well, I want a smaller false positive rate. So let's say I go over here. It's like, okay, whatever this threshold is, that will give me a 0.2 false positive rate. But you'll notice that it actually lowered my true positive rate. I went from about like 95% to about 90%, right? But that might be okay, depending on my situation. So what's really nice is that this curve represents the model. So it's the same exact model, but where we draw that threshold. And this can allow you to decide what kind of false positive rate you're okay with, essentially, or what, you know, what true positive rate. So maybe you need a high true positive rate, or maybe you need a really low false positive rate. So the most ideal, where in this graph would be the most, like the models are different, but like where in this graph would be the perfect, like the perfect model. So I'm gonna ask, is it here? Is it here? Is it here, or is it here?
Is it the top left
Yeah,
corner?
the top left, right? Yeah. We'd get like, if we got right exactly here, right, we would have 100% true positive rate, which is awesome. And we'd have 0% on the false positive, right? So that would be the perfect model, right? Now you can see is that in this case, this model does not do that. It's impossible for our model to actually do this. This could just be the fact that the data just cannot be separated. But it could also just be that our model is just no good. This is kind of like the blue is representing. This blue is representing another model that's just not very good, but it's the same data. So that's why you see this good, sorry, this excellent, this good, and then this worthless. This worthless right here, can anyone guess like what this is representing?
Random.
Random, right? Yeah, it's just, it doesn't know any different. And so this could be one of two things. One could be the model just like guessing, just like, all right, I don't know, like true, right? It doesn't know. Or it could just be like we saw where the different distributions cross over, where essentially it doesn't know any better because there's nothing to separate them out. So it has to guess. So that's why we say like this is the worst model. Note that we could technically get a ROC curve that looks kind of like this, right? Which just means it's getting more wrong than it's getting right. But essentially, if you had something like this, all you have to do is like, oh, just let me reverse that, and it would be essentially the same. So generally, you don't see ROC curves that fall underneath like this worthless line, essentially because we tend to get a little bit better and better. So you'll see closer to lines that are kind of increasing in this value over here. And note these are nice and smooth. They're not always nice and smooth, like we'll see in a second. Okay. So any questions on how this relates to our little distribution of like showing those overlap and drawing that threshold? No? Thumbs up if it sounds pretty good so far. Thumbs down, like, I don't know. Sideways, like, Okay, see a thumbs up. See Barbara, thumbs up. Cool. All right. I'll take it, Ali. I'll take Ali as a thumbs up with her screen. Okay.
Thumbs up.
Okay, cool. Thank you, Ali. All right. So it's going back to this guy right here. Now we can start seeing how these relate. So you can see I'm going to draw a really nice curve. You can see there's a little separability. And actually, I'm going to draw it a little bit so I can see this curve. So this ROC curve and this red dot is representing where we draw the threshold right here. So you can see here, if I draw it right here, I will get no false negatives, right? Our false positive, wait, I'm mixing this up. Oh yeah, our true positive rate we'll collect all the true positives, right? So this will be 100%. We collected all the true positives. So if I draw it over here, you can see like there's no, everything that's positive, we mark positive. So we have 100% on the true positive rate, right? So that's kind of like this y-axis. But our false positive rate, right, is this whole section right here. So you can see here, our false positive rate is not very good. It's pretty high. We want that to be close to 0. So if I draw this closer, you can see is that the best one, like visually, you can see, oh, we just need to draw it right here, right? So you say, oh, if we drew it right here, we would have this perfect. The thing is that this is representing what the actual like model is. And this is what, like not the model, the actual data represents. So a lot of times you might not have this full thing. So you can actually use the ROC curve to say, well, I know I want to be up here to the left if I want like the perfect model. And you can use this to say, well, okay, what threshold would make the most sense? And that way you don't have to look at a continuum like this. You can say, okay, threshold here, threshold here, threshold here, threshold here. So you might do this. And because this is, like you can see the distribution, but in reality, like we saw like only a few data points, you could do the threshold only at certain like points. So for example, if there was nothing between like 100 kilograms to 120 kilograms, you could just skip over that like 100 part, right? And say, okay, well, that's what the model would be. And this is why you'll see ROC curves usually kind of look more like steps than like this nice smooth. If you have a lot of data, you'll see much smoother ROC curves because essentially there's a lot of extra little data points. But this way we can kind of like skip around and get an idea of what the ROC curve should look like and get an idea of how a model does. Okay, so I thought this was kind of a cool way to demonstrate. And you can see your ROC curve will never do very well if you have a lot of, if it can't be separated or it's very little separation. Okay. So I'm going to move on to actually showing you guys how to make this example. So don't worry about too much about like all this extra junk right here. It is also in the curriculum. I'm just pulling in mostly data, which is why this is coming through. So note that I also designed a logistic regression so we can actually do this. So most of the stuff's actually from what we did with implementation. I'm still going to use the iris data. Okay, so I'm loading the iris data itself. I'm just basically just getting some information, and you can see I'm also just making it just one class, or I should say 2 classes. So it's like 0 or 1. So there's not multiple, or no, I'm sorry. I am using all classes. So there's only 0, 1, and 2. So know that there are 3 different classes. And so now what I can do with this ROC curve area, and this is shown in the curriculum as well, this ROC curve, which was imported from up here. You can see here from the sklearn metrics. Okay. Basically what I'm doing is like, okay, let me just plot out each model, or not each model, but how well it does for each class. So I just want to see, and that could be equivalent to like each model. Basically it's predicting, is it 0, is it 1, is it 2? And if I run this now, you'll see basically is that this right here. Oh, sorry, I misspoke. I did combine them together. So this is representing either 0 or no classes, or a different class. And you can see here, these steps are representing when there's a new point. So you can see here is that if I have a threshold at this point right here, I have a true positive rate of only like 0.2, but a false positive rate of about 0.5. And you can see here, if I go up, you can see it gets pretty, like, it's like, oh, I get all the true positives, but you can see my false positive rate is not very good. Now you can see my model is never going to do very well in this case, right? So there might be better ways for me to do this, or I need more data to collect so I can make a better curve. Okay. Doing something similar on here, I'm going to show all the ROC curves. So these are going to represent for each of those different classes. And you can see that this class, for example, is a little bit better. This might be not the best data to actually show, but you can kind of see is that it's not a nice smooth curve like always you'd expect. But the idea is that we want it closer to the left here, or at least know what false positive rate are we willing to accept, or what true positive rate are we trying to get to. Okay. So that's how you would implement this. I just kind of put it down here. Most of this is just like me trying to do deal with all of the extra, what's it called? Extra data, like little data dealing with. So I'm going to show, let's see here, example of this guy. I think this is a slightly better one. So I think it's actually from the curriculum, is it? Oh no, oh, this is from the actual this website, right? Or from scikit-learn. So we'll see what this looks like. And you can see here's a nice ROC curve. So I was like trying to pull out from iris, and like, oh, iris doesn't really show a good example. So I was just showing this part. And you can see here then, if I actually plot this out, you can see here, here's all the 3 different curves. So this is for class 0, class 1, and then class 2. So you can see here the model does a really good job of classifying class 0, right? Even at different thresholds. But for class 1, it doesn't ever really get that much better. You can see like it's always going to have a false positive rate on different parts. And so in general, it's like, okay, we might have a hard time identifying class 1. Maybe we have to apply something different to that, or we need more features, or we just accept that class 1 is just not going to be very good at being predicted. But class 0 here looks to be pretty decent. So you might say, okay, we'll accept this threshold right here and say, okay, that's about 0.9 true positive rate with about a 0.1518 false positive rate. Okay, does that make sense to everyone? At least seeing from this graph. Okay, and implementing this graph, I know it looks very intimidating by itself, but it's not that bad. It's really just a lot of the same procedure over and over again. So the curriculum also has that in the lab. You can do something similar. This is just mostly, the reason why there's a lot of weirdness right here is because I don't have my data in a nice formatted data format. I kind of had to like tweak a little things just to make it work. So just so you can kind of see it. Okay. All right. Yeah, so that is ROC Curve. That's kind of like the end of this evaluation metrics, like how we would do these things. Do you guys have any questions on ROC Curve and area under the curve? Oh, I didn't, wow, I'm really bad. So AUC, area under the curve, basically just represents saying how much area is underneath this ROC curve. That's a way to basically quantify how good is your model overall. So you can generally see, I think like from this kind of picture, it's like, oh, the light blue here, like the cyan is basically like, oh, that's like a really good model compared to like this orange down here. But sometimes there's some weird crossover too. So AUC can basically help you calculate how well it does underneath this curve. There's just another metric for you to quantify how good is this model. Okay. Cool. But now, any questions? Cool. All right, so I guess I'll go ahead and stop it here then.